Hello students, I am Satyaprakash. Welcome to Cars Physics. We are continuing kinematics and we are discussing motion in a straight line. Okay, in just previous lecture, means in lecture number 13, we have discussed ST graph, displacement time graph and VT graph, velocity time graph. Okay, in this lecture we will discuss AT graph, means acceleration time graph. So from very beginning I like to advise to students who have not gone through previous lecture, means lecture number 13, first go through it. We have discussed these two types of graphs in most easiest way. Okay, first go through lecture number 13 and then enter in this lecture. You will find very easier, not very easier, very easiest. Okay, ST graph and VT graph. Suppose just I am recalling you about VT graph. VT graph means variation of velocity with respect to time. Let variation of velocity is represented along y-axis and variation of time is represented along x-axis. So slope of graph, see, from VT graph, the slope is calculated by taking dv by dt, rate of change of velocity, and that is acceleration, that is equals to tan theta. So, variation of velocity, dv, change in velocity with respect to change in time is acceleration, and dv by dt is tan theta as we have discussed, and tan theta is slope of graph, and tan theta is equal to magnitude of acceleration. Okay, and using the value of theta we can draw different types of representation in VT graph. Suppose a body is moving with uniform velocity, velocity is constant. If velocity is constant, then acceleration is 0. If acceleration 0, tan theta 0, then theta is 0 degree. What is theta? Theta is angle made by the graph with time axis, and in this case the graph is a straight line parallel to time axis when a body moves with uniform velocity. Okay, if a body moves with uniform acceleration, means constant acceleration. If acceleration is constant, then tan theta is constant. If tan theta is constant, then theta is constant. In this case, theta is 0 degree, and in this case, theta is constant. And here, for uniform acceleration, the graph makes a constant angle with time axis, and wherever you observe, theta is constant with time axis. Okay, and if a body moves with increasing acceleration, suppose acceleration increases. If acceleration increases, obviously tan theta increases and theta increases. The graph will be a curve bending upward like this. I am representing. If acceleration increases, tan theta increases and theta increases, the graph is a curve bending upward. If you draw a tangent to get instantaneous acceleration, then this line is parallel to time axis. Here angle is theta 1, and draw a tangent here. Here angle is theta 2, and draw a tangent here. Here angle is theta 3, and so on. So acceleration increases, slope increases, tan theta increases, and theta goes on increasing, and accordingly decreasing acceleration, velocity constant, acceleration constant, acceleration increases, acceleration decreases, and we have represented all these under VT graph. And in this lecture we will discuss AT graph, acceleration time graph. Okay. Then let's represent in similar way acceleration, variation of acceleration along y-axis, variation of acceleration, and variation of time along x-axis. Okay. Again, what is slope? How can you calculate slope? Slope is dA by dt. While discussing velocity time graph, slope is dv by dt. that's equals to tan theta. And now we are discussing on acceleration time graph. Then slope of graph is dA by dt, that's equals to tan theta. So dA by dt, rate of change of acceleration. Rate of change of acceleration. Then what is name of rate of change of acceleration? Go to the most beginning class, most beginning lecture on kinematics. I have told that distance, displacement, speed, velocity, acceleration, and finally I have told jerk, rate of change of acceleration dA by dt is called as jerk. Okay, so dA by dt is jerk and dA by dt is tan theta, variation of acceleration with respect to time, and AT graph can be drawn by using slope of graph. Again, you know, acceleration is dV by dt, instantaneous acceleration. Again, d by dt, in place of velocity we can write ds by dt, rate of change of displacement, and acceleration is d square s by dt square. And here jerk is dA by dt, rate of change of acceleration means d by dt of, in place of acceleration we can write directly d square s by dt square, and jerk is equal to d cube s divided by dt cube. Okay, and unit of jerk, rate of change of acceleration is meter per second square divided by second, meter per second cube in SI. Unit of jerk is meter per second cube. Okay, and very easy. And let's have the graph, means AT graph. Let's start. Okay, so our output is jerk is equal to dA by dt, and that is equals to slope of graph. Okay, first a body moving with uniform acceleration. Body moving with uniform acceleration means here magnitude of acceleration is constant. Of course, the direction is also constant. Acceleration is vector quantity, acceleration constant means both magnitude and direction is constant. Acceleration is constant means slope of graph is tan theta, that is equal to dA by dt. If the acceleration is constant, then change in acceleration is 0, means tan theta is 0. If tan theta is 0, then theta is 0 degree. What is theta? Theta is angle made by graph with time axis, as we have discussed in previous lecture. Then here theta is 0, then the graph will be a straight line parallel to time axis. Graph is a straight line parallel to time axis. See, at t is equal to 0, let acceleration is a naught. Time increases because time can never decrease, but acceleration is always constant. Okay, this is for constant acceleration, made very easier by using slope. Okay, so graph is a straight line parallel to time axis, so theta is 0 degree. Okay, is it clear? Fine. Number 2. Second, a body moving with increasing acceleration at a constant rate. Acceleration increases but at a constant rate, means acceleration increases uniformly. Uniform increase in acceleration. So acceleration increases. Increasing acceleration at a constant rate means here dA by dt is constant. This is rate of change of acceleration. Acceleration increases at constant rate means dA by dt is constant, which implies tan theta is constant. It means theta is constant. Again, theta is angle made by the graph with time axis. So here theta is constant means the graph is a straight line making a constant angle with time axis. Slope of graph is constant means theta is constant. At any time you can observe theta is constant. At any time you can observe theta is constant. Okay. The graph is a straight line making constant angle with time axis. Clear? Body moving with increasing acceleration at a constant rate. Okay. Fine. Next. A body is moving with third case decreasing acceleration. Body is moving with decreasing acceleration at constant rate. Again, dA by dt is rate of acceleration. Rate of change of acceleration. Rate of change of acceleration is dA by dt, and body is moving with decreasing acceleration with constant rate. Okay. So here dA by dt is constant, tan theta is constant, again theta is constant, but acceleration is decreasing at a constant rate. So how can we represent it? Acceleration, let t is equal to 0, acceleration is a naught, and acceleration decreases at a constant rate. At a constant rate, acceleration decreases at a constant rate. Okay. And here, since acceleration decreases, and here negative, this is origin, and thereafter acceleration is negative. Here acceleration decreases with a constant rate. Clear? And again, since acceleration decreases, the value of acceleration is a naught at t is equal to 0. T is equal to 0, acceleration is a naught, and acceleration goes on decreasing. Acceleration goes on decreasing, and acceleration is 0. At this point, acceleration is 0 when time is any instant of time t. Okay, thus acceleration decreases at a constant rate, and here also slope is constant. Okay, fine. Then some numericals, fundamental numericals on acceleration. But before doing numericals, let's see. Acceleration is dV by dt. We know acceleration is dV by dt. So, suppose we do use this graph, acceleration time graph. Acceleration time graph. Okay. Then dV is equal to A into dt. Acceleration, instantaneous acceleration is equal to dV by dt, and dV is equal to A dt. Now integrate both sides, dV. Then integrate this side, A into. Then we may take initial velocity, final velocity, v. Okay. Then integration of dV is v. Limit is from u to v, and this is integration of a dt, and this is v minus u is equal to integration of a dt. So v minus u is change in velocity. V minus u is change in change in velocity. Change in velocity is equal to integration of at, acceleration and time, means integration of at means area under at graph. Very important. Change in velocity can be calculated by calculating area under at graph. If this is a graph, at graph, then change in velocity can be calculated by calculating area under this graph. If this value of acceleration is given and this value of time is given, then we can calculate area under the graph, means area of this triangle. Area of this triangle give us change in velocity. 2 is here. Okay. Fine. This is one concept. Then another concept of acceleration. dv by dt. Again, acceleration is equal to dv by dt into I may write ds by dt. Sorry, ds by ds. dv by dt. Acceleration is dv by dt into 1. In place of 1, ds by ds. Then acceleration is equal to dv by ds. dv by ds into ds by dt. Then acceleration is equal to dv by ds into v, and finally we may write v dv is equal to ads. Okay, v dv is equal to ads, and you can now integrate both sides. V dv is v square by 2. You may put limits from u to v, from u to v is equal to integration of ads. So here we are getting half v square minus half u square is equal to integration of ads. So if you multiply mass, then it is half mv square minus half mu square is equal to m into integration of ads. Integration of ads. Have you remembered this concept? Change in velocity is equal to area under at graph. This is very important. Keep it in your mind. Okay. Change in velocity can be calculated by calculating area under acceleration time graph. Very important. Then integrating both sides and putting the limits from u to v, we got half v square minus half u square. Just multiply mass in left side, mass in right side. Then this is final kinetic energy. Final kinetic energy, because final velocity v, initial velocity u, and this is initial kinetic energy is equal to m into integration of ads, and change in kinetic energy. Final kinetic energy and minus initial kinetic energy is change in kinetic energy per unit mass is equal to ads. Thus, change in kinetic energy per unit mass is equal to area under AS graph. AS graph. A is acceleration, ds is small change in displacement, and A into ds means area under acceleration and small ds, small displacement ds, and by integrating we can get total area under acceleration and displacement graph, AS graph. Thus, change in kinetic energy per unit mass can be calculated by calculating under area under acceleration and displacement graph, AS graph. These are basic concepts and highly useful also. Okay. Then some numericals. Keep this in mind. Only one or two numerical, easier numerical, and I hope you will enjoy the numericals. Suppose this is question number 1. A graph is given. A graph is given. Variation of time, variation of acceleration, acceleration in meter per second square, and time in second. Okay, and here acceleration is 10 means 10 meter per second square. 10 meter per second square. Acceleration is constant. Acceleration is constant up to time 10 second. Okay, up to time 10 second. This time is 0 and acceleration is 0. Again acceleration is constant. Again acceleration is constant up to time 20 second. Let this value of acceleration is minus 8. Sorry, this value of acceleration is minus 8 meter per second square. Okay. From this given graph, we have to calculate. Question is given like this: calculate velocity at t is equal to 20 second if initial velocity of a body is 5 meter per second. Just graph is given and question is asked. By using the given graph, calculate velocity at time 20 second if initial velocity is 5 meter per second. Initial means when time is 0, velocity is 5 meter per second. What do we know? Area under AT graph gives us change in velocity. Means area under AT graph. Let's take A. Area under AT graph gives us change in velocity, means final velocity minus initial velocity. Area under AT graph gives us change in velocity, final velocity V minus initial velocity 0. Then final velocity is equal to U plus area under AT graph. Initial velocity U plus area under AT graph. This is the method. Then now it is made very easier. Say this area is A1, this area is A2. Again acceleration is vector quantity, positive plus, and this is negative minus. Then how can you calculate final velocity? Initial velocity is 5 meter per second. Then area under graph A1 plus A2, no, A1 minus A2, because this is for minus 8 meter per second square. This is positive, this is negative, and here this is 5. Area A1 plus area A1 is 10 into 10 meter per second square into 10 second, and this area minus, this is also 10, 20 second minus 10 second in 10 second, and again this side is from 0 to 8 means 10 into 8, 10 into 8, and calculating this is 5 plus 100 minus 80. 100 minus 8 is 20, 20 plus 5, 25, and unit of velocity is meter per second. 2 is here. Thus velocity at 20 second is 25 meter per second. Okay. And another one, easier numerical. Can I erase it now? Okay. Suppose this is a given graph, acceleration and time. The graph is like this. This is 0. Okay. And acceleration is represented along y-axis, time is represented along x-axis. Okay. Suppose here acceleration is 10 meter per second square and This is time. Let here time is 20 second. Okay. And here time is 22 second. Okay. And what is asked? It is asked what is velocity at 22 second if initial velocity of a body is any value you may take 2 meter per second. Try it first. If initial velocity is 2 meter per second, what is velocity of the body at 22 seconds? It is also very easier in similar way. See, this area is A1, this area is A2. See, if this angle is theta, then this angle is also theta. This area is A. Okay. Then our form, what is our form? Final velocity is equal to initial velocity plus total area. Then U plus total area is A1 minus A2. This is in negative. This acceleration is negative. But what is this value? We don't know. What is this value? We don't know. You just see. This value is A. In this side, this value is A. Then theta is same. This angle is 90. This angle is 90. Then how to get this value of acceleration? See. Tan theta is equal to perpendicular upon base. Here perpendicular is 10, base is 20. For this triangle, tan theta is equal to perpendicular, let A, or along y-axis you may take y, A, divided by base. This is base 20 second to 22 second. So this is 2 second. A by 2. Okay. Now we can equate 10 by 20. Tan theta, 10 by 20 is equal to A by 2. So acceleration is 1 meter per second square. Now it is easier. Final velocity, initial velocity is 2, and this area A1 is half, base is 20, height is 10, minus A2 half, base is 2, this is 2 second, base is 2, and height is A is found to be 1, half, 2 into 1. Is it clear? Then final velocity is 2. This is 10 into 10 plus, this is 10 into 10, 100 minus 1. Then 102 minus 1, 101 meter per second. I have taken arbitrarily any value, and this is just a method to explain how to attempt the numericals. And these are we are finding easier. Okay. Thanks. In next lecture again we will have some beautiful discussion. Thanks my children. Thanks.